Welcome back. I am Dominic Clevey. I teach at Central Washington University. Today's lesson is on parametric equations. For most of our life, most of the time you have spent in mathematics class, most of the time you have spent graphing functions. You have graph functions that look something like y equals something with an x in it. Y equals sine of x, y equals 3x squared, y equals some of them have been very complicated. But they've always been based on the idea that y is somehow based on x, that y is a function of x, that y depends on x. It turns out fairly often in the real world, it's not the case if you have two variables that one of them depends on the other or the second one on the first. Sometimes the relationship is quite a bit more complicated than that. And to give you an idea of what's going on, I want to turn to what's actually somewhat silly of an example. It's an example that's often used in statistics classes for a slightly different purpose. Today I want to use it for our purpose, to demonstrate why you might be interested in something like a parametric equation. I realize I haven't told you what a parametric equation is yet, but don't worry too much. Let's see if we can understand what's going on. And I'd like you to consider the following set of data. Alright, can we see the computer screen? Yes, excellent. So on this computer screen, and I can make these figures a little bigger for you, I have some data from the United States from the 19th century. For each decade in the 19th century, we can measure the number of doctors who are practicing in the United States and the number of arrests for public drunkenness in the country during the same time. Now, this might seem sort of strange. It might not be clear why doctors and public drunkenness are together, but what I want to do is take this data and I want to show you what it looks like if we graph it. Isn't that what we always do with data, if we can? Let's take the two different figures that we have, doctors and the amount of drunkenness. Let's plot these. And what happens if we plot them? Well, if we were to look really close, we'd see that this isn't a perfectly straight line. Some of these are a little bit higher and a little bit lower than others, but it's almost a straight line. And if we were to draw this in a nice way, if we were to find an equation for this line, we could do it. We're good at finding equations that go through lines, and we could come up with an equation that looks like y equals some constant times x, maybe plus a small constant, though it looks like the y-intercept is close to 0, so it might simply be something like y is 2.2 times x. What do we make of data like this? If we take our normal equation, if we find that y equals 2.2 times x, that maybe means something like amount of drunkenness is 2.2 times number of doctors. Maybe it's the case that throughout the United States and throughout time, there's always been about twice as many arrests for public drunkenness in any given year as there were doctors. And if that's true, what does that mean? Does it make sense to say that the amount of drunkenness depends on the number of doctors? If you have more doctors, are there necessarily more drunks? Is it the doctors themselves who are going out? Or maybe it works the other way. Maybe it's the case that if there's a lot more public drunkenness, that means people are sick, and that means we need more doctors, and so more doctors come. Which of them do you think it is? Do doctors cause drunks? Do drunks cause doctors? Or perhaps is there something else going on altogether? And I will tell you whenever a teacher says, is the answer A or B? The answer is so often a little of both, or maybe a third choice altogether. And so it is here. There is a third choice. What's going on here with this data is something else very important in the United States throughout the 19th century. What happened between 1800 and 1900? Well, the country got a lot bigger. New states were added. A lot of people were born. A lot of people immigrated here. The population went up dramatically. And as the population goes up, so do the number of doctors. As the population goes up, so do all sorts of arrests. So do all sorts of births and deaths. So do people going to school. And among these arrests that we can talk about is, of course, public drunkenness. Neither of them depend on the other. They both depend on a separate parameter. They both depend on time. And if we want to understand this relationship, we would do well to understand it by thinking about both of these things as a function of time. It will turn out this is a very powerful concept. The idea that we can leave the old y equals x, function of x, environment, that we can go to some place new where both x and y are changing over time, and where they both depend on some new constant, some new t. There's another very classic example of this. I'm going to now amuse you all by trying to draw a picture, which I've never been able to do well. This is Jimmy the tall shot putter. Jimmy's arm is so high it's 6 feet in the air when he throws his shot put, and he's found it's best to throw it at an angle 35 degrees from the ground. It turns out physically there might be angles that if you go even higher than that, but Jimmy's arm is strongest at 35 degrees, and this is the angle that he would like to use. Now, if we were to go down to the physics department and ask them, they would tell us that we can plot the x-coordinates and the y-coordinates of the ball as a function of time. It's not, of course, that y depends on x. Does the height of the ball really depend on where it is? It's not really that x depends on y. Both of these, the height of the ball and the distance that it's gone, depend on something different, depend on how long the ball is in the air. In fact, the physics department could help us pretty explicitly. The x-coordinate is written as something like this, is 88 times the cosine of 35 degrees times t, where t is the number of seconds. And the y-coordinate is 6. That 6 is going to represent the original height from which Jimmy threw the ball. 6 plus 88 times the sine of 35 degrees times t minus 16 times t squared. What can we ask about this now? We can't exactly write y as a function of x. There might be a way, of course, that we could figure out how to do that. But what else could we do? Well, immediately we might ask something like, where is the ball after 2 seconds? And one of the beauties of the parametric equations is it's really, really easy to find this. To find this, what do? Well, we simply plug in t equals 2. The x-coordinate is 88 times the cosine of 35 degrees times 2. And the y-coordinate is exactly what it should be, is 6 plus 88 times the sine of 35 degrees times t minus 16t squared. It might be easier for us to use this equation if we use decimal approximations for our sine and cosine functions. Why don't we call up a calculator and rewrite these in a way that might be nicer. We had 88 times the x-coordinate was cosine, so times the cosine of 35. And I think we should probably be very careful, of course, that we are in degree mode. We are currently in radian mode. Radian mode is the best place for your calculators to be most of the time, isn't it? Mathematicians love radians way more than degrees, but physicists sometimes like degrees, and this is a physics problem. Alright, so let's leave the menu. Now if we hit this, it looks like we can rewrite this equation as 72, and there was a 2 at the end. We needn't worry yet about this. Secondly, we have, let's check this other one out, y was, we had an 88 times the sine of 35 degrees. Which is 50.47. So we have 2 new values now, of 72.08 and 50.47. It maybe wasn't necessary for us to find this, but I suspect if we write it this way, this might be a bit easier. Now our x-coordinate will simply become 72.08 times 2. The y-coordinate is 6 plus, remember this whole value is 50.47. 50.47 times our t is 2 minus 16 times t squared. T is 2 in this case. I must remember this at every step. Minus 16 times 2 squared. The x-coordinate, therefore, is 144.16. The ball has got 144 somethings. We weren't very careful in this case to specify what the units are, though I can tell you by looking at this equation the units were feet. So why don't we accept and hopefully believe that we planned that from the beginning. This is the number of feet. The second one is a little bit trickier, but 50.47 times 2 is about 101. 101 plus 6 is 107. 107 minus 64 is 43. So if we did this math right, the ball, after 2 seconds, is still 43 feet in the air and has gone 144 feet. Jimmy, in other words, is, among other things, a world champion shot putter. Perhaps we should go back and make him a right fielder. Nevertheless, we know very quickly we can solve problems, complicated problems, using these equations. Let's ask for something even more difficult. I want to rewrite the equations that we had, especially the simplified versions. X is about 72.08 times t, and y is 6 plus, this was approximately 101t, minus 16 times t squared. Let's take these equations and ask another question. How far will the ball go? How far will the ball go? What does it mean to ask how far the ball goes? I guess what we're really asking is when it hits the ground, how far has it gone? Can we calculate that? I'll tell you, this is a very popular quiz question for this sort of equation. You can answer this question, you can do pretty much anything. So let's think about this. The ball stops when it hits the ground. It hits the ground when the y-coordinate is equal to 0. When the y-coordinate is equal to 0. So first, what do we need to do? Well, all we have to do is find the t. That makes the y-coordinate equal to 0. Can we do this? Can we take this equation and solve it and set it equal to 0? Of course we can. We could use a quadratic equation, but since we have a calculator right here, let's make life easy for ourselves and pull up a solver. Here we have a TI-84. The easiest way to do this actually is probably just to graph this. Shall we try? If we have 6 plus 101 times a variable x minus 16 times a variable squared. If we graph this, and clearly if I'm going to graph this well, we need to be able to get rid of the dots, which are here from a previous lecture. Pardon me. And we want to turn the plots off. Will this work any better for us? Looks like this will work better for us as long as we have some idea what the value is. If we don't know, we might start with a pretty standard zoom. We'll set the window to be what it is at a basic starting point and see if we can see some place of what's going on. And now it looks like we did. It looks like the ball's going to go way up in the air and hit right down about here. Indeed, I suspect we can now calculate exactly where the value is. I want to find the 0, and we know it's somewhere between x equals 2 and x equals 10. I don't use these calculators very often, and most of you can probably do this more quickly than I can. Let's also remember all we're doing here is finding the 0 of a quadratic equation. There are lots of ways to do this, and none of them are right. Please feel free to do the one you find best. But we found it now. The y-coordinate is equal to 0 when the variable t, it's t in what we've written before, is equal to 6.37. Let's go back to our equation and look at this and see if we can make sense of this. Y equals 0. Remember, this is what we want to find. Y equals 0 when t equals 6.37 seconds. The ball he's throwing will be in the air for 6.37 seconds. That's a long time. We have a talented thrower in our gym. How far does the ball go in this time? Well, now this should be fairly easy. We can take our 6.37 seconds. We know that's how long it's in the air. We can plug it in. We know the distance it's gone at any time x is equal to 72.08 times time. And so if we multiply these, we should be fine. The ball travels 72.08 times 6.37 is equal to 459.15 feet. Note the calculations we're doing are not particularly difficult. The only big idea here, the reason we cover this separately, the reason there's a section in our book called parametric equations is this big idea, this exciting idea, this powerful new idea that x needn't depend on y, that y needn't depend on x, that perhaps they can both depend on some new thing. Now, if that's true, we might find some really great things. After all, think about any function you might care to draw. If you draw a function, what happens? Well, you get a line, it sort of curves, it shoots up and down at various times, but for each value of x, there's only one value of y. That's what makes it a function. Once we lose that requirement, once we're allowed to do more things, once we're allowed to vary both in terms of a third parameter, it turns out that, among other things, the graphs we can make are amazingly cool. I'll show you some beautiful ones here before we're done. I want to start with something that's not amazingly beautiful, but just sort of nice. However, let's think about finding the equation of an ellipse. You all remember what ellipses are. If we have some sort of axis, an ellipse is this thing that looks more or less like an oval. It's a circle which has been skewed in some way. Where circles always have the same radius, there's a sense in which an ellipse has two radii. I can call one A and one B. And the formula for the ellipse is something that we've often seen before, though most of us probably don't remember. It doesn't come up very often. X squared over a squared plus y squared over b squared is equal to 1. And by varying the values of a and b, what we'll do is change the ellipse to make it narrower and longer to change its orientation. Already we know we're looking at something here that's not a function, right? Y is not a function of x here. It doesn't pass the vertical line test, for example. And clearly, there's more than one value of y for most of these values of x. Nevertheless, we have a nice equation for it. We have an equation not y as a function of x, but an equation that uses both x and y. It turns out that the standard form of the equation of the ellipse, is only one way to represent them. Let's consider an ellipse in parametric equations. What if x is 6 times the cosine of t and y is 3 times the sine of t? I'd like you to take a moment right now and think about what it might mean to have these equations. We're letting t vary, so t is getting bigger and bigger. And as it does, x is always equal to 6 times the cosine of t. If you can picture the cosine graph in your head, when t is 0, the cosine of 0 is 1, so x is going to start at 6 and is going to get smaller and smaller and smaller. Meanwhile, y is going to start at 0 and get bigger and bigger and bigger. So the x-coordinate should be dropping down, the y-coordinate should be going up. You can almost imagine starting here and following exactly this. We start with an x-coordinate of 6, and the x-coordinate will get lower. At the same time, my pin is going up in the y-axis, and the y-coordinate is getting taller. It'll be true until this point, and y should start coming down again. And I think if we think about the sine function, think about pi over 2, we'll agree that, in fact, sine starts to go down again after pi over 2. These are the equations of the ellipse, but I want to turn these into rectangular coordinates. I want to turn these into standard coordinates. I want to turn these into the one that we're used to. Can we convert these to standard form? You might rightly ask why we're doing this. Don't we already have standard form? Well, we do have a standard form here, but this standard form covers all possible ellipses. Remember we said the particular values of a and b determine the precise shape of the ellipse. And so we could ask then, which values of a and b do these correspond to? I want to know which ellipse this is that are described by these parametric equations. What do I do to convert this to standard form? I do one of the most important tricks in parametric equations, which is called eliminating the parameter. The way we've currently listed our equations, remember these are x equals 6 cosine t and y equals 3 sine t. They both depend on t. Can we write them in a way that they don't? Can we get rid of them? Can we somehow make them go away? It's a tricky thing to do. How do we take these equations and put them together in some sense where they can go away. And one trick that we can use, somehow we can do this if we remember sine and cosine, take sine and cosine of a variable, what makes it go away, and what sometimes makes a variable go away is this wonderful equation we've all come to know and love, which is that cosine squared plus sine squared is equal to 1. What can we do with this then? Well, let's say we have x over 6 is cosine t, and y over 3 is sine t. And if we think about these equations and think about our cosine squared plus sine squared, it might be pretty obvious what to do. I already know that cosine squared t plus sine squared t is equal to 1. And since cosine squared t is this, I have immediately that x over 6 squared plus y over 3 squared, sine t of course is y over 3, is equal to 1. And this is exactly the ellipse I'm looking for. I now know which ellipse we have. We have the one that corresponds to an x value of 6 and a y value of 3. We know how wide the ellipse is, how tall the ellipse is. We can read it directly off of this. Alright, that's nice to do. It's something we somewhat often do. We eliminate the parameter and try to write all of this in terms of just x and y. But it's not always possible. And this shouldn't surprise us, right? Of course it's not always possible. If it were always possible, we wouldn't have had to come up with parametric equations in the first place. What's the point of inventing a whole new concept of mathematics if it doesn't let us do something that we couldn't do before? And so, not always is possible. Sometimes, in fact, we get very nice things we couldn't get any other way. And one of the fun parts of parametric equations is playing with these, of making graphs of things we couldn't make graphs of before. I found a few of these I want to share with you. I think we have some of them stored right here. And there are several ways to graph this. Your calculator can graph these things fairly well. If we switch the mode of the graphing, let's put ourselves on radians again. Let's change ourselves to PAR for parametric plot. We'll find that we can do some pretty interesting things. Right here in the graphing, instead of it saying y equals and looking for some function of x, there's x as a function of t, and y is a function of t. And let's start with one that's a little bit boring, but nice enough to have fun with. Cosine squared t and sine squared t. Here we're going to have, did I say squared? Cosine cubed t and sine cubed t. Thank you. Sine of t squared cubed. And here we'll do cosine of t cubed. And let's graph this and see what it looks like. Well, it looks fairly boring here in this screen. Everything that's going on is right down there, and we can't tell what's going on very well, but we can zoom in and try this again. You can almost tell it's more interesting. Let's zoom in one more time. Alright, now we've cut out the corners, so we have some sense of what this looks like. It's this beautiful little diamond shape. Diamond shape where all the edges bend in a little bit. It's a shape unlike that which we've really seen before. It's new, it's fun, and it's pretty neat to work with. In fact, they get much better than this. I want to show you at least one more, which is sine 10t, sine 8t. Let's go back here and see if we can erase what we had. I need to get rid of my extra cubing up here. So let's put in the sine of 10 times t. And I never like it much for missing a parenthesis at the end. We can make this the cosine of 8 times t. And again, try to get rid of the cubed. What does this look like? There's something else we should think about, which is what are the values of t we're going to plot. Let's not worry too much about that right now, but we will have to soon. And we see it doesn't even want to let me graph it with this thing up here. I wish some of you were here with me to help me fix this. Looks like this is working fine. Let's scroll back over, highlight this, and delete our power. And if we do, Looks like we'll be able to graph. We need to zoom back out now. Alright, here's an example of what we can get. It's a nice picture. It's still not entirely clear what this picture looks like, but I suspect it's something very different than what you've had before. Now, I told you I was bad at using these graphing calculators. I don't use them much. I don't use them for graphing at all because they're better tools. And before the lecture is over, I want to show you one of these. I want to show you these because it's way more fun to do parametric plotting if the things look pretty. And this thing is something that perhaps you have seen before. It's a website called Wolfram Alpha. In fact, a quick search engine will find it for us. Wolfram Alpha is a wonderful tool if you haven't used it before. It's a powerful calculator. It's a device for looking up all sorts of facts. It's something that I really like to use in classes and like to show students things that they can do. One of the things it does is plot things. It plots, for example, parametric equations, and I have one of the commands right here. If you want to use this yourself, it's easy to find in Google. And if we simply type in parametric plot, it'll do a plot. It'll do a graph using parametric equations. And here are the two coordinates. X is the first one, Y is the second one. This is an extra thing we're allowed to add if we want to that says, what are the values of t we're looking at? You could imagine, of course, that there are lots of different choices, right? As long as x and y depend on t, you could let t get as big as you want. We thought about the ball in the air example. We said we wanted t to keep going until it hits the ground. We wanted to figure out where that t is. Here we'll go from 0 to 2 pi, just because we're doing angles. We're doing sine and cosine, and we know these things usually start repeating by then. Let's plot this now and see what we find. And here's the picture you're trying to find on the calculator. Isn't it beautiful? Isn't it cool? There's a lot of great stuff we can do now that we can do parametric plotting. In fact, now that we made it quick, let's do at least one more. I won't read this to you. If you desperately want to find it later, you can pause the movie. But here we have this wonderful little starburst shape. In fact, by tweaking your coordinates and your constant values here, you can make a starburst shape of however many points you want. And parametric equations are not something we need to spend much time with in a pre-calculus course. They are something that will come up again in future courses, in calculus classes, in physics class, and it's nice simply to have some intuition for how these things work. I would encourage you to spend time playing with this. There's no better way to get a feel for it than to pull out your calculator or to pull out a website like this Wolfram Alpha. Try punching in various things and see what you can do. Your book, at the end of your section in the homework, will have several other examples of beautiful shapes that you are encouraged, that you are welcome to try out. But that's all that we have for now. So with this, thank you.